Hello again. This is the second video about the topic of function analysis and graph. This time I'm going to show you how to find the slant asymptote of a function. If you remember the elements of a function, a restriction domain, x and y intercepts, the symmetry, vertical asymptotes and empty dots, horizontal or slant asymptotes, the graph, and the range. So I'm going to show you an example where I'm going to find everything and then explain how to get the slant asymptote. Here, in this example, the function is g of x equal to x squared plus 1 over x minus 1. The first step, remember the domain, is the denominator has to be different than 0, so x minus 1 different than 0, x different than 1, after isolate the x. So the domain is going to be x belongs to all the numbers except the element 1. For the second step, the x and y intercepts, the x-intercept, you need to equal the whole function to 0. So we pass the denominator, it becomes 0 to the other side. X squared plus 1 equal to 0, which is the numerator. So then we isolate x squared equal to minus 1, but then you have x equal to square root of negative 1, which is an imaginary number, so it doesn't exist. So that means that there are no x-intercepts. For the y-intercept, the x has to be equal to 0, so we have the function g of 0. We evaluate, we have 0 to the square plus 1 over 0 minus 1. We evaluate that, so the answer is minus 1, so the y-intercept is 0, minus 1. For the symmetry, we're taking two values, the value of 2 and the value of minus 2. Why? Because those two values are not my restriction, so there shouldn't be any problem with that. G of 2 will be 2 to the square minus 1 over 2 minus 1. We evaluate that, so the answer is going to be 5. Then we have g of negative 2. We evaluate that, the answer is minus 5/3. If you observe, the two values are totally different, value and sign. That means that the function g of x is not symmetric. Step number 4 about the vertical asymptotes are on empty dots. If you remember, we only have one restriction, x equal to 1. Therefore, we check the limit, the full limit at that value, limit x approaches 1 of g of x. We evaluate that and we obtain a number over 0, so it doesn't exist. So that means that the value is going to be a possible vertical asymptote. That means that we need to check what happens one from the left and one from the right. We evaluate that in the function. We have then 1 plus 1 is 2, that doesn't change. Then we have 1 from the left minus 1. So we have 2 over 0 from the left, and that's equal to negative infinity. Then we have 2 in the next one, 2 over 1 from the left minus 1, 0 from the right. 2 over 0 from the right is equal to infinity. It's a tendency. Therefore, since at least one of them goes to infinity or negative infinity, then x equal to 1 is a vertical asymptote, and since that's the only restriction that we have, there are no empty dots or gaps. For the horizontal asymptotes, if you remember, the procedure says that you need to evaluate the limit at infinity and negative infinity. We evaluate in the function, which if you remember, this one, this is the function, we evaluate the limit there. So we have infinity over infinity and infinity over negative infinity. In this case, for example, we need to check the degrees for the short procedure. In the short procedure, we see that the degree of the numerator is greater than 1 of the denominator. Therefore, the answer is going to be infinity and negative infinity. Now, the thing about the negative infinity, you need to be very careful, is because when you evaluate at the beginning, the sign matters. So to be careful with that. But if you're not sure of this, or which sign is going to be either plus or minus, I recommend applying the long procedure, that is dividing by the highest power in the denominator. So, since we have infinities and not numbers, there is no horizontal asymptote. Then, After this, we have, or after we don't have horizontal asymptotes, we need to check if we have a slant asymptotes because that's the condition. In this case, for the slant asymptote to exist, if there is no horizontal asymptote, but the degree of the numerator is just one more, like for example 2, 1, or 3, 2, one more, the degree of the denominator, then you may have a slant asymptote. So in the example that I show you, there is no horizontal asymptote and the degree of the numerator is just one more than the degree of the denominator, so there's going to be a slant asymptote. But how do we do it? Well, here's the thing. There are two procedures to find it. A long procedure and a short procedure. For the long procedure, you need to apply the following limits. To do what? What a slant asymptote is going to be a line, a linear function, a function of the type mx plus b, an inclined line, the ones that you saw in Math 2. So you need to find the value of m and the value of b. And for the value of m, you need to find a limit. The limit x approaches positive or negative infinity, one of them is enough, of the entire function divided by x. That is, apply the function, divide everything by x, and then simplify and get the value. The value of v is the limit x approaches positive or negative infinity of the function minus the slope that you found times x. It is a little complicated, so I'm not going too much into depth for this one. So what I'm going to do is show you the alternative way, which is a lot simpler. The alternative procedure to find a slant asymptote is using long division of polynomials. I'll show you an example in a moment. That is, divide the numerator by the denominator. To obtain what? Well, the division. Numerator divided by the denominator equal to a certain quotient, which is going to be a function, plus the remainder of the denominator. That happens if you divide. So in this case, the quotient, this expression that you find, is going to be the slant asymptote directly. Example. In the same example that we're working with, we know that it's going to be a slant asymptote, so we're going to divide the numerator over the denominator. How? Well, this is the numerator, this is the denominator. We're going to use long division of polynomials. You saw that in Math 1. So how do we do it? Well, will be the numerator x squared plus 1, but we need to complete with a 0x, the term that is missing for the polynomial, divided by the denominator, which is x minus 1. So we divide. Remember, to divide, we take the first term, x squared divided by x, so we have just x. Then multiply x times x squared, x times minus 1 minus x. We subtract that, so we cancel x squared minus x squared, eliminates 0x minus x becomes positive x. Then you lower the 1. Then again, x plus 1, sorry, divided by x minus 1, so it'll be 1 because we're dividing the first term only. X divided by x is 1, and then multiply 1 times x, 1 times minus 1, so will be the subtraction of that, x minus x is 0, and 1 minus 1, which is plus 1, will be 2. But for the entire division, the only thing that matters for the slant asymptote is the quotient, the answer. So the slant asymptote is going to be that quotient, which is going to be a line, y equal to x plus 1. That is the slant asymptote. And that will be for any kind of function where you have a slant. And remember, the condition for you to have a slant is that there is no horizontal asymptote and the degree of the numerator is just one more than the degree of the denominator. If it's more than that, then no, there's no slant. It's another thing. Now, with all the information, we're going to graph. Remember, we need to plot the x-intercepts, y-intercepts, etc. Let's go step by step. You remember the x-intercept, there wasn't x-intercept. There weren't x-intercepts, and y-intercept is 0, minus 1. So 0, minus 1 is the y-intercept. Vertical asymptote is x equal to 1, which is this one. There is no slant, there's no horizontal asymptote, but there is a slant asymptote. So the slant asymptote y equal to plus 1 y equal to x plus 1 is this inclined line. Remember, to graph an inclined line is the y-intercept and the slope. The y-intercept is plus 1, so just put a point of the slant, which is here, and then the slope, which is 1, is from this, just 1, 1, 1, 1, 1, 1. I recommend that you use square paper for this. You put just the slant, and then to graph the function, you need to cross the point and just follow the shape given by also by the behavior before and after the asymptote, which is before the 1 is negative infinity, after the 1 is positive infinity. So that means that you go before the 1 negative infinity, after the 1 positive infinity, and then that's that. And then the range, in this case the range will be a little difficult to find it because you need to use derivatives for that, but in this case it's an approximation. So this will be minus infinity to minus 0.83 included, which is this value, union 4.83 comma infinity. And that will be the range. Okay, that will be all. Thank you very much. See you in class.